What specific problem does LLM-Microscope aim to solve in the context of understanding large language models? And how does this problem relate to the opacity of LLMs?
LLM-Microscope aims to address the problem of understanding the internal mechanisms of large language models, LLMs, which remain largely opaque, making it difficult to interpret how they process contextual information. This opacity limits researchers' ability to enhance model performance and understand the reasoning behind predictions. By providing a comprehensive framework for analyzing and visualizing LLM behaviors, LLM-Microscope enables the inspection of how models encode and aggregate contextual information, thereby bridging the gap in understanding. The toolkit includes methods for contextualization assessment, token-level nonlinearity measurement, and intermediate layer analysis, which collectively reveal how LLMs utilize seemingly trivial tokens, such as stopwords and punctuation, as key aggregators of context. Ultimately, LLM-Microscope seeks to make the internal workings of LLMs more interpretable, facilitating improvements in model design and application.
How does the proposed method or algorithm, LLM-Microscope, work? Please illustrate it step by step, highlighting the major components and processes involved in analyzing LLMs.
LLM-Microscope is a comprehensive framework designed to analyze the internal processes of large language models, LLMs, through several key components and methodologies. First, it allows users to select from various pre-loaded language models and input custom text for analysis via an intuitive interface. The major components include a visualization dashboard that generates heat maps and graphs to display token-level nonlinearity, layer-wise contributions to token predictions, and contextualization levels of each token. The analysis process involves collecting hidden states for each token across all layers, applying a language model head to obtain token probabilities, and computing prediction errors to track how predictions evolve through the layers. Additionally, LLM-Microscope employs techniques such as measuring token-level nonlinearity and assessing contextual memory by reconstructing prefix information from token representations, ultimately providing insights into how different tokens encode and retain contextual information. This structured approach enables researchers to uncover patterns in LLM behavior and improve model interpretability.
Can you provide a simple yet illustrative example of how LLM-Microscope analyzes token-level nonlinearity or contextualization? Walk us through this example, detailing the main steps and how they illustrate the algorithm's capabilities.
LLM-Microscope analyzes token-level nonlinearity and contextualization through a systematic approach that involves several key steps. For token-level nonlinearity, the framework computes the linearity score for each token by applying a generalized Procrustes analysis between adjacent layers, quantifying how closely transformations can be approximated by a linear mapping. For contextualization, the model processes an input sequence to collect hidden states for each token across all layers, then uses a trainable linear pooling layer, followed by a two-layer MLP to reconstruct prefix information from individual token representations. The effectiveness of this reconstruction is evaluated using cross-entropy loss, where a lower loss indicates a higher degree of contextual information retained by the token. This process allows LLM-Microscope to identify which tokens are most effective at preserving context and how their nonlinearity varies across layers, showcasing the framework's ability to provide insights into the internal workings of LLMs.
What are the theoretical or practical benefits of using LLM-Microscope compared to existing methods for interpreting large language models? Are there specific performance metrics or advantages that are noteworthy?
LLM-Microscope offers several theoretical and practical benefits over existing methods for interpreting large language models. Firstly, it provides a comprehensive framework that includes tools for contextualization assessment, token-level nonlinearity measurement, and intermediate layer analysis, allowing for a more nuanced understanding of how models process and aggregate contextual information. Notably, It enables researchers to visualize token-level nonlinearity and contextualization scores across layers, which can reveal critical insights into model behavior that traditional probing methods do not capture. Additionally, the framework demonstrates practical implications by showing that the removal of seemingly trivial tokens, such as stopwords and punctuation, significantly degrades performance on benchmarks like MMLU and BABILONG4K, highlighting the hidden importance of these tokens in maintaining coherent context. This performance drop, even with careful removal strategies, underscores the utility of LLM-Microscope in enhancing model interpretability and efficiency, making it a valuable tool for both researchers and practitioners.
How was LLM-Microscope validated or tested? Discuss the experimental design, datasets used, and the benchmarks or metrics for performance that were applied to demonstrate its effectiveness.
LLM-Microscope was validated through a series of experiments that focused on the impact of removing filler tokens, such as punctuation and stopwords, on the performance of language models. The experimental design involved two main benchmarks: MMLU, which tests factual recall and reasoning across various subjects, and BABILONG4K, which assesses long context reasoning with significant distractor text. The study employed several token removal strategies, including naive rule-based removal and a more nuanced approach using GPT-4o to selectively remove tokens deemed safe to delete. Performance metrics were based on accuracy scores from these benchmarks, revealing that the removal of seemingly trivial tokens consistently led to a drop in performance, particularly in tasks requiring extended context. This demonstrated the effectiveness of LLM-Microscope in highlighting the importance of contextual signals stored in filler tokens.
What specific results were achieved with LLM-Microscope, particularly in relation to task performance and the insights derived from its application? Be sure to highlight any data or findings that support the conclusions drawn in the paper.
LLM-Microscope revealed that removing seemingly trivial tokens, such as punctuation and stopwords, significantly degrades performance on tasks requiring specialized knowledge and long context reasoning, as evidenced by the consistent drop in accuracy on benchmarks like MMLU and BABILONG4K. Specifically, the analysis showed that even a careful removal strategy using GPT-4o led to performance losses, underscoring the hidden importance of these filler tokens in maintaining coherent context. The findings indicated that determiners and punctuation marks were the most contextualized tokens, while nouns and adjectives were the least, suggesting that language models utilize less significant words as key aggregators of memory. Additionally, a strong correlation was found between linearity and contextualization scores, indicating that tokens with high contextualization correspond to more linear transformations across layers. This comprehensive analysis provided critical insights into how LLMs process and retain contextual information, ultimately enhancing our understanding of their internal mechanisms.